everybody, my name is Ivan Raikov. I'm a postdoc in the lab of Ivan Šoltes at Stanford University, and we work together with Gerd Hieber from the HDF group on developing a parallel large-scale I/O workflow for our simulations. So initially the project proposal was to develop a graph representations for the neuronal networks we simulate, which are typically represented as vertices and edges. But then as we realized that HDF was quite suitable for our purposes, we also sort of started converting more and more of our data formats to HDF. So we ended up using, we developed a HDF format for the neuronal morphologies, and we are also now in the process of converting the output data of our simulations, which takes the form of voltage traces and spike event times to HDF. So we have so far developed a library which we call Neuro.io, which uses parallel HDF5 to represent the connectivity and the morphological structures of the neurons in our network simulations. And of course, it interfaces the neuron simulator, and of course, all of it runs on blue waters. So basically, a typical neuronal network model consists of a number of neurons which tend to be in different populations, which represent different biological classes of neurons, which each have their own sets of equations and parameters. The network tends to be sparse. So in this example, we have over 300,000 neurons, which could potentially be quadrillions of connections, but in reality, only about 10% are connected. So this network has about 3 billion edges. There are specific rules, so most neurons prefer to connect with neurons that are nearby and with a few long-distance connections, so the networks are generally sparse and small-world. So we devised a format for representing sparse graphs, which we call the destination block sparse connectivity format. And the idea is that the sets of edges are organized in blocks so that each block contains approximately the same number of edges, which seems to improve load balancing. And in addition, the format is centered on destination vertices, which have associated with them the source vertices of all their incoming edges, as well as an arbitrary number of numerical attributes associated with each edge. This helps us instantiate the simulations in the neuron simulator, because in computational neuroscience, when you instantiate a connection, you want to instantiate additional equations on the receiving side. So it's a little bit perhaps counterintuitive if you don't know this. But of course, in memory, we can instantiate the graph in any format we want. This is just how the HDF layout is. We came up with a sparse graph format that consists of 4 HDF data sets. Essentially, the idea is that for each block, we want to know which are the indices of the vertices in the edges contained in that block. So we have a sequence data structure that tells us the indices of the destination vertices in the block, and then several pointer structures that tell us for a vertex S, what are the locations of the source vertices of that? So this is pretty similar to sparse matrix formats, except we add another layer of indirection so that we can structure the edges in terms of blocks. And then in the actual HDF layout, of course, every HDF file has a root element. We organize the connections by projections, which in neuroscience jargon is the set of connections between 2 groups of neurons. We have a number of projections representing each type of connection in the biological system. The 4 data sets that actually describe all the edges, and we have a sufficiently flexible scheme to encode additional attributes for each edge, such as synaptic weight, distances, and a few other things that are helpful with analysis of neuronal network graphs. So our initial, our legacy data format, so to speak, was MATLAB files that we exported text files from those, and then we loaded them in the neuron simulator. So yeah, it was pretty horrible. So basically using HDF, we achieved great improvements. we converted this graph, which had 1.1 million vertices, 39 projections, resulting in 2.7 billion edges. So the size of the graph, as represented in text files, was 120 gigabytes, and a compressed HDF file was just a little less than 10 gigabytes. And this also included additional numerical attributes. So it wasn't hard for us to achieve very dramatic improvements using HDF. And further, after the edges are read into memory, of course, we need to have some ways to distribute them to the compute ranks. So we followed a pattern where a small number of MPI processes are designated for I/O operations. They use the parallel HDF library to load chunks of connectivity, and they instantiate the edge set data structure, which is the in-memory representation of the graph. And they use MPI pack and unpack to serialize these structures, and then MPI O2OV to actually distribute all of the edges to the compute ranks where the neuron simulator runs. MPI O2OV is very flexible, but of course there are some drawbacks when one uses a large number of MPI processes. So our initial performance measurements showed that the I/O time stays, so we conducted measurements with 64 I/O ranks and up to 32,768 compute ranks. The total absolute I/O time stayed constant when reading the graph, which is not surprising as we use 64 a constant number of I/O ranks. However, the time to actually instantiate the network started increasing after 16,000 ranks, which is probably due to which is almost certainly due to network communication and our use of the O2OV collective operation. And it wasn't very easy to actually compare this with the performance of the legacy model, because since we were using these horrible text files, if we wanted to instantiate a simulation with 32,000 ranks, we would have had to create many, many text files. So I didn't attempt to benchmark beyond 2,048 ranks, just because we were starting with we basically didn't have parallel I/O when we started the project. And then another component of this project was to perform graph load balancing. So in a simulation of a neuronal network, generally speaking, if all the neurons receive the same number of connections, then we don't need to worry about load balancing, because we're going to have approximately the same number of equations associated with each connection, with each synapse. But in the graphs, in the networks we're dealing with, there could be, some neurons could have up to 10,000 connections, some could have maybe 2,000. So this could result in a lot of imbalance during the simulations. So we investigated several strategies to perform load balancing just based on the connectivity of the model. So first we started with a naive round-robin assignment scheme, which is this one. We then attempted to implement a greedy placement strategy of vertices according to the mean in degree for each rank, which resulted in some improvement. But after some discussion with the developers of the neuron simulator, we came up with a strategy which takes into account the computational complexity of each neuron, which is roughly corresponds to the number of state variables. And in addition to that, we also consider the in degree and a greedy assignment, greedy placement. So this resulted in pretty reasonable load balance for short simulations. So in yellow is the greedy assignment algorithm that uses both cell complexity and in degree. In red is the greedy algorithm that only uses in degree, and blue is the round-robin strategy. And as you can see, when using 32,000 ranks, actually everything converges. And part of the reason is that these were short control simulations. In reality, if we had longer simulations with more complex input patterns, this probably wouldn't look like this. But I really couldn't run very long simulations just for load balancing. And then the last component of the proposal was to perform graph analysis, which we really ran out of time. We explored several libraries. We considered several graph libraries for this purpose. In the end, just to do a certain kind of graph neighborhood analysis, we came up with a fairly simple algorithm inspired by some libraries such as Pregel and GraphLab. Essentially, we do a sequence of all-to-all operations to first distribute the input set to all the ranks, do the graph analysis computation, and then send the results back to the respective owners of these vertices. This is probably not very efficient for algorithms that require a lot of iteration, but so far it's kind of working for us. The assumptions, of course, that we have balanced edge counts on all processes for this to work efficiently, and generally associative commutative operations. So this is not very general yet. We hope actually to be able to interface to graph analysis libraries that use GPUs, but some solutions we considered don't really have support for using a lot of GPU cards yet, although it will probably happen soon. And finally, even though this wasn't in the original proposal, we also implemented a representation for the meshes that represent neuronal morphology. These take the form of 3D points that are also connected by graph edges, topological edges, with a corresponding HDF structure, which has data sets for all the 3D points, and then some pointer offsets that tell us where the points for each neuron ID start. And the HDF representation of our initial conversion for 1 million cells and about 1 billion points resulted in a 7 gigabyte compressed HDF5 file, and of course ridiculously large text files. And then we have been extending this with additional attributes for synapses, the locations where connections are made. This has resulted in a total file size of about 24 gigabytes compressed HDF. So loading these cells in the neuron simulator, so again, the I/O time stays constant because we use a constant number of I/O ranks. The actual loading time also involves using a steady state solver to find the steady state voltage of the cells. And because this happens serially, the curve looks like this. But still, compared with the legacy code, which we couldn't even run for more than 2048 ranks, this is a pretty substantial improvement. Now we can actually scale pretty well as we increase the number of ranks. So finally, conclusions. Our collaboration with the HDF group has drastically improved our workflow and I/O performance. And by that I mean we didn't even have parallel I/O when we started. So that's pretty good. The HDF5-based infrastructure also has led us to develop this sort of a parallel Python iterator that allows us to generate graphs and update the connectivity rules for our graphs and regenerate them in a matter of a few hours, whereas before it took weeks. And even though the paid program has helped us tremendously, we still, perhaps it would be nice to have some level of support for taking this software further and maturing it and perhaps making it more general for a wide range of use cases. And finally, I want to thank members of our lab, Stanford University, of course, Blue Waters, and everybody who has provided us with technical assistance, the HDF group, and these are our funding grants. And I wish to thank, of course, the PRAC program. And that's it. Thank you very much.
All right. We have a quick